Perfect. Okay, round of applause to the tech crew. I couldn't be more happy to be here in Sweden, screwing up, Swedenland, isn't that this? Okay, sorry. Of Krause, we are here in Switzerland, home to big confusions like what flag do Spotify even use to celebrate their IPO for, right? Stupids. I am Tobias Due Munk, and I'm from Copenhagen in Denmark, and I'll just keep pacing through this if everything is working with the setup now. Maybe. Stefan is waving. My audio is too loud. I scream too loud. I'm really excited now because this is fun. Okay, so I'm here to talk about depth APIs available on Apple's platforms. It's showing false color. The colors are not that good. Okay, don't worry about that. So it's under the title Into the Deep, and I always wanted to have intro music when walking on stage. So I don't know. We need more music, right? Just a little bit more. That's good. Okay, so we're ready for the first topic. Live streaming depth data is what I'm going to use in this talk. You can also get depth data when you are snapping photos as single frames. Most things that I'm going through here will be applicable to both domains. So let's just keep pacing through this. Most parts of Apple's APIs for depth are in AV Foundation. Maybe I shouldn't pace this much through this. Capturing is for iPhone only, but manipulation of the data can also be done on Mac and on tvOS. So like the three big performant-ish platforms. Both the front camera on the iPhone X and the dual camera of the iPhone X, as well as the two less plus-size iPhones, with their dual cameras, can capture depth. Here we set up a discovery session that will work on those devices. For a discovery session, we can ask for devices, and then we can select one of them with some random pick one function, and then we upgrade it to a device input, and we add the input to the AV capture session. Then we want the output as well. We create a depth data output, add it to the session, and then we set the delegate. It's a very deep delegate. Okay, so the code is a bit too wide. It's quite shitty. A lot of the APIs are just... So excuse me for very liberal use of line breaks. I hope the code is still just at least somewhat readable. So this is the same function, just squashed even more. I wouldn't submit this in a pull request ever. But what you can see here is the callback for the depth data outputs, and the depth data is the main one that we are concerned with here. So let's take a look at what it contains. So AV depth data is backed by a CV pixel buffer. This buffer might be familiar to you if you've worked with images or videos on Apple's platforms before. If you haven't, fear not, we'll go through it. This buffer is almost like the other buffers, but not quite. The format is a little bit peculiar. So one thing you can do is we can convert the depth data to a float 32-bit format that has a Swift native type, and then we can then each pixel in the buffer will then just have one value. So it's not like with RGB where you have multiple values per pixel. Here we just have the single one. And here we are creating a function that can read a single value in the pixel buffer. This is a lot of C-styled APIs. Kind of have to. It's a bit more low level. The first thing we do is we cast it to a buffer, the buffer to an array of floats. And then we have to remember to lock the buffer, and we also calculate the position because it's an array and not a 2D map. Based on the width of our buffer, and then we end up having our value from the CV pixel buffer. And we also need to introduce just a little bit new terminology. It's just one word. It's disparity. Disparity, as you can see here, it's the inverse of the distance, also known as the depth. And a value of 1 for both of these equals 1 meter. So it means that for disparity, it will increase above 1 when it gets closer to 1 meter, and decrease when you're going away. Yes. And be sure to name things right. Like often when you have, like when you get the depth data and you ask for the depth map, you actually get disparity. So Apple's APIs are not so good at naming it, but make sure that you do it so you're sure if you're working on one or the other, because they're completely opposite. I find it very easy to get confused about this, at least when I'm working on it. I'm actually considering my talk should maybe be called Into the Disparity, but I don't know if that makes any sense at all. So let's see it in action. And here we go. There we go. So here you can kind of see my face coming out of the screen. This is what it is. Hi. Okay. As you can see, we need the visuals, we need the audio, else nothing of this works, right? So let's do a quick comparison between the true depth camera that's on the front of the iPhone X and then the dual camera that are on the backs. This is, just as before, when using the true depth camera on the front. It's iPhone X only, for now. It uses an infrared transmitter and sensor, so it works in dark. And if we compare this to the dual camera on the back, then maybe I can actually do the thing where I'm videoing Paul. Like it might be difficult to see, but you might see some kind of, can Paul wave? There you go, there's Paul. Nice. Maybe we should do someone else. No. Okay, so the data here is really artistic when you have stuff in front of here. So it's inferred from the stereo effect from the two cameras. It also means that it performs really bad in low light, particularly when we are live streaming like we're doing here, making it pretty useless for live streaming, but for static photo captures, it's or like single shot photos, that it works quite well. But for live streaming, for some reason, it's just not so good. Okay, next topic. Depth capture has a fairly limited amount of settings. The most important one is filtering. Here, filtering is disabled, so you can see when I'm in view, there are some black spots in the data where the sensors didn't get proper reading. So we just get a NaN value back. And if I'm holding my arm like this, you might be able to see there's kind of like a shadow effect below the arm. And that's because the sensor and the transmitter for infrared is they're not located in the same position on the front of the phone, so it has like a shadow thing that you can't see. So it's kind of like your right eye is sending out light and your left eye is looking at it. Then there's stuff that you can't see, and that's basically what's like on the lower side of obstacles. Okay. You can also see here when I'm moving my hand really close to the screen that it breaks. It can only detect distances when it's above like 20 centimeters. I don't know how much it is in feet for you guys, like 20 feet, 40 feet, I don't know. Probably the same, right? Like this amount of distance, like maybe. Okay, it's less than 1 feet. Okay, so it's good when I'm itching my nose, you can actually see it on the big screen. Genius. So when filtering is enabled, this one, you can see that all the spots now are gone that we had before. You can also see that it breaks differently when I'm moving my hand close. It's kind of like, instead of NaN values, it just goes back to having like very infinite distance values instead. Besides just doing some sort of like live interpolation, they're also doing temporal filtering. And for some setups, like if you have stuff that is not so easy to detect in the background, here is quite easy because it's a nice surface. But then it might fail, and you can see some temporal artifacts. What you also lose when you're adding filtering is that you lose all the information about what sensor readings are actually not valid. So you might want to roll your own filtering instead of using this one, because it's definitely not it has some trade-offs that you need to consider. Let's add a bit of color to the mix. Just as for depth, we can request video output from AV capture session. This is quite standard. It has been there for quite a while. The setup is exactly the same as for depth. We're adding an output to the session, and we're setting the deep delegate again on the video data output this time. And the delegate callback is a different one than from depth. Therefore, AV Foundation has a convenient synchronizer, so we don't have to mess with these multiple delegate callbacks because they might be called in like an unpredictable order. Okay, so the error message that just arrived up in the right corner was perfectly timed for my demo. Maybe. What happens is that the depth sensor runs hot, like really, really, really hot. Now we are at level yellow. There's also orange and red. I hope that my phone can go through the entire talk without blowing up. Else we need to have Patrick up here blowing on the phone or something, like just to cool it down. Maybe some ice from downstairs. Okay, so what you can see here with the synchronizer, back to that one. I should mention, every time you hear that sound, there's something changing up in the right corner, and you can kind of follow along. So if everything else is boring, just see how many times it changes. Okay, so for the synchronizer, we are adding our outputs here and here. So the data output and the video data output we add to the synchronizer, and then we just set our deep delegate to the synchronizer, and then now we have a single callback that gives us synchronized data when coming back. The main part here is the data collection. And yeah, I'm truly sorry for the line breaks, if they make any sense, like you feel like you're in Objective-C world again with all this stuff. But that's how it is. I told you the code lines could get Krause deep. So yeah, that's just how it is. Here we have a data collection that we are looking into. Data collection has subscripting implemented, just like a dictionary, and it uses the data outputs as keys for the subscripting, and then the values we here also cast to our expected types of data. A lot of vague casting, kind of annoying, but that's how it is. And then, depending on the use case, did you get it? We might want to discard all the data. So if just one of the two sources is dropping a frame, we just drop everything, because else we have unaligned data. We often don't want that. And then, despite all the broken lines, line-broken lines of code, we finally have depth data and video data perfectly aligned. That's what you see here. Okay. So let's give the depth module a little break. It could really need it. That's good. I used to be a dancer for 10 years. No. Okay. So you might be wondering, like, what's up with the resolution? Was tech really this lo-fi in the 80s? No. Okay. So here I'm digitally zooming in on my left eye. And this doesn't really show the full extent of the resolution. So let's go one step further along the scale of using embarrassing facial features and projecting them up on a very, very, very big screen. This is my nose. And what you see here is the raw data. So you can kind of see it's actually quite nice. It doesn't see all the dimples and stuff. But it's VGA resolution. Yeah, I need to cover up my nose so it doesn't zoom in on it. And then for the TrueDepth camera, it's VGA. But for the thing on the back, the dual camera, then it only does QVGA. But as I mentioned, the quality of that was really low anyway. Now it's just, you know, like even the resolution is lower, but the quality is also really low. There you can go. There you go. Now you can see it. Good. Okay. So before we're going deeper into the depth data itself, let's have a look at higher level APIs that uses the depth sensor, importing ARKit. It's iOS only. It has a setup structure that is very similar to what we saw for AV Foundation. Yay. We create an AR session, we configure it to give us face tracking output, and then we set the delegate, but this time we set it on the session and not on the configuration or the output objects. It works for the TrueDepth camera on the front of the iPhone X only, this face tracking feature. So here we have the delegate callback. This is the same callback that is used for things like plane detection and image detection. The demo that was shown previously by A2 showed that kind of how image detection and plane detection worked. Or image detection is probably the one that he's using for that one, like the supermarket guiding system. This callback provides a vaguely typed array of AR anchors that could be then image or plane or, in our case, a face anchor. And these are all synchronized, so we don't have to use a synchronizer and that kind of low-level stuff to make it work. Here we try to map, using new compact map, to map the type to the AR face anchor, and we just expect one match, so we're just picking that one. And what you see here is, again, my face, all the time just my face. I'm rendering a geometry property that is on the AR face anchor, and it includes all the animations, all the changes, anything. Like, I'm doing nothing besides rendering the geometry in 3D. And the perspective is a little bit weird. It's not really the shape of my face unless you're really close, like actually this close. So if you want to try it out later, just come this close to my face, and you can see that it's actually a really nice representation. It actually does change the shape based on your face. So I tried it on my kid that has a more round, low kind of face, and it turns almost completely round. So even though it doesn't adapt to all different facial features, it does kind of squish around a little bit to match it. So it can be used for many things. The AR face anchor also has some more detailed values than just this big geometry. It has something called blend shapes. These values are what powers animojis that you're most likely familiar with. There are like 50+ values for things like brow position, eye position, the nose, amount of nose sneer, and how much you're squinting on each eye. So like a lot of small different detail values. Blend shapes, they're just a dictionary of legacy NS numbers. So what you see here is we're basically waiting for a 90% duck face, and then we capture the perfect selfie. I think this is maybe the most valuable piece of code. Like you have an app here. Like this is an app. Like I will, like if you don't build it, I will build it. Like go build it. Just let me know before I build it, and give me half the money. Okay, so here's just like a small music demo using the blend shapes to adjust the sound of some of the music. You might see sometimes the frame rate seems to be dropping and stuff. It's probably just because of my implementation. You can make it work quite smoothly if you do it right. Probably enough of that one, right? Okay, so in the very beginning, I showed you how to convert a CV pixel buffer to contain Swift native floats in the interest of performance. Let's look at how we can read the raw data that we get from the AV depth objects directly, skipping the conversion. It turns out that the data type of this is disparity float 16. 16-bit float is a half float, and it's not available in Swift Foundation or whatever thing it should be said is not in. It's not available in my Xcode, is kind of my description of it. So it's 16-bit, and float is usually 32 bits, so it has less resolution than a normal float, so they can pack it smaller. So I went online to figure out how to parse this, and I put the magic inside two convenient functions, like just extensions. The first one is for going when you have the value in the big pixel buffer, and then you can get a half float value from it, and it contains the magic. The other one is for going the other way around if you have a floating value, and it's of course just reverse magic of Krauss. So just imagine some bit shifting going on along with like some exponent significant calculations that really took a while for me to figure out. We are now adapting our getter method from before to just read the data directly. So this is supporting reading a CV pixel buffer that hasn't been converted into float 32, but just reading the half floats directly. The first thing we do is we here cast the uint to a uint 16 instead of an array of floats, as you can see far up there. And then the only other change is that when we then have our value in the end, we then convert it to, or read it to be a half float, which we know that it actually is. So now we can read a single value from the CV pixel buffer without having to convert the entire buffer first. So an example for how to use this kind of getter function that's just like peeking into one pixel, let's use the depth sensor as an input device. That's not so good. There we go. OK, so what you see here is I'm just calculating a position for sampling a pixel on the left side of the screen, on the right side of the screen, or the depth camera view. And then I can use my hands to kind of change those values. So a left disparity and a right disparity. And as you can see, we use our getter to get the values in the buffer. Here I'm just changing the note that is played depending on if the right hand is closer than a certain distance. It's bigger than 2, so it means that because it's 1 over depth, well, you do the calculation of what the distance is. And then we have the left disparity that we're using to change filter characteristic depending on the distance of our left hand. So that's what we get here. This is the relaxing time for me in this presentation. So just keep going, right? Maybe it's too relaxing for you guys as well, so don't fall asleep. So a typical thing that you might want to do when you're working with depth data is that you want to normalize it. It's very typical that when you're showing a preview of some any type of data, you want to normalize it so people can see the full contrast of the data, and you also don't want any of the data that is presented in whatever, if it's a graph or whatever it is, to be clipping. So this is basically the same thing we're doing here. We're just normalizing the CV pixel buffer to go from a value of 1, from 0 to 1, or the other way around, depending on how you look at it. It might also be necessary or useful for whatever processing you want to do on the depth map, that you want to do various things. It might make sense to kind of jump into normalized domain before doing further processing. The first thing we need to do, or we need to create to be able to normalize the data, is to have a setter to put the values back into the buffer. This is very similar to what we saw before. That's the reason for stuff just being commented out. The main difference is that we use our half float API to create a valid bit pattern from a floating value, and then we just store that bit pattern back into the buffer at the correct position. So we don't suddenly add non-compatible data into the CV pixel buffer. So here is the first part of the normalize function. It's very textbook example, just looping over all the values, all the pixels, sorry, in the buffer, and then we find the minimum and the maximum values. This code is so tedious that there's probably bugs in it. And then we can now adjust the values in the pixel buffer to normalize it using our new setter function. Again, just looping over all the pixels and then doing the calculations, setting the values back into the buffer. So this is showing the data without normalization. And what you can see here is that if I'm closer to 1 meter, that's this much. Other people that don't know meters, ish, like something like, I don't know. Does anyone know how to, like, a perfect metric says the size? No, everyone knows what it is, right? OK, so you can see everything is white from about here. And then when I'm getting closer, stuff is still white. So now I'm enabling normalization. And you can see now that I'm basically staying white all the time, or clipped, like just barely clipped. and when I'm moving closer, the normalization adapts, and if I'm holding my hand up, you can see that it's still like keeping the entire range of the data inside. So this is really useful for visualizing depth data, so you don't just show something that has very basic gray values, like very centralized. So you can see this is without normalization. It's kind of faded, and when I'm adding it, you kind of expand it and have a higher contrast. So it's much better for previewing depth data. One thing I didn't do in the example that I showed here, but I do in the code that is running right now, is that don't lock and unlock your buffer for every single read and write of each pixel in the pixel buffer. Just do it once for the entire thing. Saves you quite a lot of time, or CPU power. You might also notice some, I don't know if you can, like this, there are barely any drop frames in this one beyond the depth sensor not giving that high frame rate right now because it's yellow up there. But it does use quite a lot of CPU performance to do the thing that is running right now on the phone. So despite reading raw data, we can do even better for normalizing. Sorry for that one. So we can just not read raw data and let core image do it. Also, we can let core image perform the normalization. This uses the GPU, so it's also often more performance, or at least you're not doing stuff on the CPU, so it might also even be more energy conserving. Core image works quite well for depth data because it knows how to read half-floats. So even though Swift doesn't know half-floats, core image and also even Metal knows what half-floats are. Please give them in Swift Foundation. OK, so core image is available on the 3 big platforms. It's definitely one of my favorite frameworks, so I'm really happy to be able to use it here in this talk. A core CI image can be fed a CV pixel buffer directly, so initialization is really quick. As before, we need to find our min and maximum values before we continue to the normalization. So there's a new filter called CI area min max, which is created for disparity data or depth data, which stores the result in a 1 pixel value, because that's how core image works. And this filter is nicely not documented by Apple. So if you pay attention to anything, or just one thing in this talk, maybe it should be this thing. OK, so we take the output of that filter and we render it to an array using a CI context. We notice how the format is KCI format RGH. And it means that it contains 2 values for each pixel, and we only have 1 pixel, and both of them are half-floats. The first value is red, and it means the minimum value, and the other one is, the second one is green, and it means the maximum value. Once again, our half-float implementation comes in handy. OK, so now, finally, we can normalize the data based on these min-max values. We're using a CI color matrix filter to do it. The math is the same as before, or it's different, but it does the same. And it's just to accommodate the way that the color matrix filter works. And now we have a normalized output just as before. And I've even added some rain in the background, right? So it's better than the other one. OK, so you might not see that big a change in frame rates. You do definitely see the temporal artifacts sometimes here, like when I'm moving around. But at least I can promise you that the CPU usage is way lower. Yeah, thumbs up for core image. So let's go a little bit further in core image to see what we can build with it, just to show you some examples. I only have 2 examples left before the talk is done, so bear with me. I'm not showing the full code here. Basically what it is, the filter is set up to do is to create 2 slopes that we before kind of used to normalize data. Now we just use it to kind of add a gradient to it. We blend the 2 slopes together, and then we have an effect like this. So you can kind of see we're zooming through the depth data. You can kind of make like Terminator-style scanners doing this thing. Here I'm adding another filter on top, and what you have now is basically something very similar to what Halide is using in their camera app as an overlay on. I shouldn't stand out here looking, then it's just boring, right? OK, so it's basically the same thing that Halide has in their camera using as an overlay on the viewfinder to represent depth data. So like they're showing the color image live normally as what a camera app does, and then when you have depth capture enabled, it shows something like this overlaid on top, so you can kind of see if the depth data captured is kind of looking what you're expecting. It's a quite nice effect they've created, I think. Okay, and finally, a very common thing to use depth data for is to blur the background of a photo to make it look more pleasing. And portrait mode is just that, and it's built into the stock camera app. The filter behind portrait mode is CI depth blur effect. It just takes a color image, and it takes, I'm doing it again, right? Like scratching my eye. Okay. It takes a color image and a disparity image, give it to it, and then you just have a blurred photo. And this is the fun part because the app just crashed. There it is. You can see the background being blurred. That was good. OK, so it defaults to focus on the face. You can see if I'm moving my hand in front here, my face still stays in focus. And you can see when I'm moving my hand in front of my face, it doesn't detect my face, so it's just focusing on whatever is closest, like the closest object in the picture. So that's the fallback when there's no face in the photo. We can also do as I'm doing here, which is basically setting a specific focus area that it should use for focusing on. It's an input focus rect, it's called. It has to be wrapped in a CI vector. And you also have to remember to Y-flip it, because this is similar to macOS, I guess, and it's not what we use to an iOS. So if you're translating from a tap to something that should be focused in the filter, then the user would kind of see unexpected behaviors. If you tap in the top, then you focus in the bottom of the image. So remember this. Orange. Wow, that was not good. Only one step more to go. Back to yellow. That's good. OK, so now it focuses on the rect, and it disables the automatic face detection. The focus is fixed on the top left of the image, so I have to use my right hand, I think. Yeah, there we go. It looks very easy when I'm doing this right, but it's actually very difficult. OK, so this is fun. But you can see that it's just focusing on that thing up here, no matter where it is. So if it's the same distance as my face also becomes in the same focal plane, so it's also in focus. OK, so the CI depth blur just has this is the last thing. It has a setting for changing the blur radius. It's called aperture to mimic DSLR lingo, and here it is set to 22. It has an inverse relationship to the blurriness, so the background is not so blurred with this value. But if I'm moving really close, you can see that the background, or you might be able to see that the background is still just a little bit blurred. Here I'm switching to something that is in the other end of the spectrum. So it has an aperture of 1. You can basically not get a camera that does that. That is not a very, very, very big and expensive one. And here we just fake it, so that's easy. You have a very shallow depth of field, and that's all I have for you today. So just a few references. Tutorials and guides online always is a huge help doing anything. Thanks to Simon Gladman, personal hero of mine, Ray Vendelich, and Dragos Holban. They have some stuff that I used for this talk. The Halad camera app is really, really, really awesome. You can export depth maps from it, so if you don't want to dive into code immediately, but just want to look at data for like depth data and see how it is and what you can do with it, play with it in Photoshop or whatever, buy Halad, support them, and then you can export your depth data from there. I made an app called Slur that uses the last filter, like from the last example, so you can edit portrait mode photos. Ping me on Twitter, handle that I haven't showed, to get a promo code if you want that one. The Mac sounds used here I found on a website called Pingy, if anyone could recognize those Mac sounds. Open source is always a big reason why we can work efficiently as developers. And it's also a big source of being able to learn stuff. So here is a shout out to 2 frameworks that I used specifically in this for this talk. AudioKit is really awesome if you do audio. if you heard something that was choppy in this thing, it's mostly because of the way that I've done stuff, and I didn't, I'm not a pro in that one yet. And then there was an app called How that is also open source that inspired me to figure out an implementation for the format filter. And as a small gesture, here's a link to the implementation of the half float. So just write the last thing down before I go to the next slide. And it's open source today. Or maybe it was yesterday, I don't know. OK, so thanks very much to Stefan for dealing with me for this setup. And thanks again very much to the tech crew and to Patrick and everyone. I've been a difficult one, and hopefully it was worth it. Thank you.